science review sheet. So it looks like this on one side, there's an atom, and on the other side there's a guy skateboarding. So this is all of 8th grade, or most of what we did this year in 8th grade, in one paper. So let's start over here. We have an atom, and it has different regions, region A, region B, and C and D. Which region shows where most of the mass of the atom is? Most of the mass of the atom is right here, in the nucleus. So this in the middle, this region is called the nucleus of an atom. This is where most of the mass is. So region D. Okay. What is that region called? We just said it. It's the nucleus, or the center of an atom. An atom is mostly empty space. Okay? That's one of the features of an atom. Most of it is just, there's nothing there. It's mostly empty space. The particles, remember there are 3 particles, protons, neutrons, and electrons. The particles of an atom that can be gained, lost, or shared in a chemical bond are electrons. Electrons are the part of an atom that can be gained or lost in a chemical reaction. Alright, let's label this atom really quick. So inside the nucleus we have protons, P+, and we have neutrons, N0, because they have 0 charge. And then outside the nucleus we have electrons. So these are electrons, E-, because they have a negative charge. And then we need to know or remember the electrons that are farthest away from the nucleus. So this one, this one, this one, and this one. These electrons have a special name. These are called valence electrons. Alright? These are the electrons that can be gained or lost or shared in a chemical reaction or chemical bond. To find the number of neutrons, you have to do the atomic mass, and you have to round it to the nearest whole number, minus the atomic number. Okay, so let's look at this element argon. Okay, this is the atomic number. It's always the number on the top. And this is the atomic mass. The atomic number is important because this tells you how many protons there are, and it also tells you the number of electrons. It's the same. Okay, so argon has 18 protons. Protons are the same as electrons, so it has 18 electrons. Negative because electrons have a negative charge. To find the number of neutrons, we have to do the mass minus the number. 39.9, is that closer to 40 or is that closer to 39? You have to round it. Because that's greater than 5, we're going to round up to 40. So you're going to do the atomic mass, which is 40, minus the atomic number, which is 18, and this is how you find the number of neutrons. So that's going to be 22 neutrons. Okay? So you need to know, just by looking at a box like this from the periodic table, how to find protons, electrons, and neutrons. Okay? For valence electrons, if you want to find out how many, remember valence electrons, I'm going to write valence E negative equals group number. Alright? If it's in group 1, it has 1 valence electron. If it's in group 2, it has 2. Argon is actually in group 18, which means it has 8 valence electrons. You can't have more than 8. So group 17 has 7, group 16 has 6, group 15 has 5. Alright, let's keep talking about atoms a little bit. So here, when you have different elements like this is called a compound. When elements combine, they make a new substance called a compound. Okay, How many atoms of magnesium, or Mg, are there? Mg is right here. There's no subscript here, but there's this 2 here. This 2 has to be distributed or multiplied by everything before it. So this gets multiplied by 2, and this gets multiplied by 2, and that's it. This 2 only distributes to what's inside the parentheses. There's no coefficient here, so like we can just put like a 1 here, but you don't have to. So how many magnesiums are there? There's only 1. Okay, this 2 does not multiply magnesium, so there's only 1 magnesium atom. How many atoms of oxygen, or O, are there? Okay, right now I see 3. Okay, but you have to multiply this 3 by this 2. So 3 times 2 equals 6. So there are 6 oxygen atoms in this compound. Just for fun, how many nitrogen atoms? There's none here. There's no subscript here, so there's 1. But this 1 has to multiply by this 2. 1 times 2 is 2. So if you want, you can write N equals 2 atoms. There's 2 nitrogen atoms. And remember, if I ask you how many elements are in here, every capital letter is a new element. So capital M, that's 1 element. Capital N, that's another element. Capital O, that's another element. So this compound has 3 different elements. For it to be a compound, you need different elements. If I just have like, you know, N2, that's not a compound. That's just a molecule. A compound has to have more than 1 different element. Okay, this should be familiar. The law of conservation. Conservation means something is kept the same. The law of conservation of mass says mass cannot be created. You can't create an atom, or destroyed. You can't destroy atoms. It can only be rearranged. Okay? So if I go on a field trip and I take 20 students on this field trip, 20 students have to come back. That's what this law is basically saying. If I start with 20 grams of something, I have to end with 20 grams of something. How many grams of chromium? Chromium is Cr, so they're talking about this one over here. How many grams of chromium should be formed in the chemical reaction below? It says, oops, circle the reactants. Reactants mean ingredients. And we find them to the left side of the arrow. Okay? And underline the products. The products are on the right side of the arrow in a chemical equation. So the reactants are, this one is a reactant, and this one is a reactant. So these are my reactants, my ingredients. I mix those 2 together and I get my 2 products. It says underline the products. So these 2, aluminum oxide and chromium, these are my 2 products. Okay. How much did I start with? I had 76 grams and 27 grams. So total 76 grams plus 27 grams. I start off with total 7 plus 6 is 13. Add the 1, 7, 8, 9, 10. So total, the total mass of my reactants was 103 grams. If I start with 103 grams, I have to end with the same. That's the law of conservation of mass. I have to end with 103 grams. If I know the mass of one of my products is 51 grams, what must the mass of this product be? That's what this question is asking you. How many grams of chromium should be formed in the chemical reaction below? If I start with 103, I have to end with 103. And I have 2 products. So in order to find out the mass of this one, I have to subtract it from the mass of this one. So I have to end with 103 grams. I already have 51 grams. So 103 minus 51 grams, 52 grams. So that means this one must be 52 grams in order to end with 103 grams. So law of conservation of mass, if I start with 103 grams, I'm going to end with 103 grams. So this one must be 52. Zinc can combine with other substances. Okay, so if I do like zinc plus oxygen, it'll make, maybe zinc oxide. That's what they mean. Zinc cannot be broken down into simpler substances. So if I have zinc, I can't break it down into something smaller. I can't do that. Zinc is an example of an element. We know it's an element because it has its own little box on the periodic table. Zinc. Okay? You can't go anything smaller than zinc. Alright. Building on our knowledge of atoms, we remember that matter can change in two ways. You can change chemically or you can change physically. Alright? The key thing to remember is a chemical change, you're creating something new. Okay? Something new. And a physical change, nothing's new. You might change the size and appearance, so nothing new. So things you can change in the physical change are things like size, shape, or appearance. Okay? So, burning a match. Anytime you have fire in there, it's a chemical change, because I cannot unburn a match. So that's a chemical change. Breaking a twig. A twig is a stick. So if I have a stick and I just, break it in half, it's still a stick, right? I'm not changing it. It's just two smaller pieces. So that's a physical change. If I were to burn that twig or stick, that would be a chemical change. Making mud with dirt and water. Okay, this one's kind of tricky. If I mix dirt and water and I make mud, you're not changing the dirt. The atoms in the dirt aren't changing, and the water is still water. Okay, so this is an example of a physical change. Okay. Dissolving Kool-Aid and water. So everything you're doing right here, these are called mixtures. A mixture is when you can combine something and you can sort of uncombine it if you want to. Okay. So dissolving Kool-Aid in water, that's a physical change. Anytime you have some sort of mixture, like dirt and water making mud, Kool-Aid and water making Kool-Aid, those are physical changes. Breaking glass into pieces. If I have a mirror and, I shatter it into like a million pieces, it's still glass. So that's a physical change. Ice melting to water. If I have a solid ice cube, okay, ignore that ugly picture, and it melts into a puddle of water, the ice is made out of frozen H2O. The water is H2O. I'm not changing anything. So anytime you go from a solid to a liquid or from a liquid to a gas, any type of phase change, that's a physical change. Because I'm not changing the atoms. I'm just changing the state of matter from solid to liquid. Okay, did a chemical reaction occur? Remember the four signs of a chemical reaction. We have a temperature change, color change, a new solid or precipitate, and some type of gas bubbles or fizzing. So, bubbles are formed. Did a chemical reaction occur? Yes, because of the bubbles. After mixing two clear liquids, the solution is still clear? No. Okay, there is no color change. Temperature remained constant or the same? No. If it's the same temperature, that means there is no chemical change or chemical reaction. A new smell comes from a carton of milk, like when it gets spoiled. Yes, because something new is occurring. It's a chemical reaction. There is a change in color. Sometimes spoiled milk looks a little darker, okay? And there's something new. There's like bacteria in there that's making it smell bad. After mixing two clear liquids, a yellow solid appears at the bottom of the test tube. The fancy word for a new solid, which you might see on the SOL, is called a precipitate. A precipitate. So, a new solid is formed. Yes, a chemical reaction or a chemical change occurred. Okay? Alright. How can you separate a mixture of salt and water? So if I have a beaker filled with water and I put salt in there, how can I separate it? I can add heat. If I add heat, the water will evaporate. And what's going to be left? The water vapor is going to be outside, so water as a gas is going to be outside, and then the only thing that's going to be left inside is sand. So the way you get water and salt separated is you evaporate the water by adding heat. Evaporate water with heat. Okay. This is rock candy. It is sugar water. So they took water, H2O, and they added sugar. Again, anytime you add two things together and you get like dirt, water making mud, or Kool-Aid and water making Kool-Aid, that's called a mixture. So sugar and water together, sugar water is a mixture. A mixture is something you can separate. Okay? If we wanted to separate the sugar from the water, we can evaporate it. Okay. In a mixture of salt and water, what is the salt? Okay, remember these words: solute, solvent. Okay, and then remember the little trick. The loot, like the treasure you steal, goes into the vent to hide it from the cops. So the loot, the solute, goes into the vent, the solvent, whatever you're dissolving it into. So, what is salt? Salt is the solute. It's what you're dissolving. What is water? Water is the solvent. It's the thing that's dissolving. Water is sometimes called the universal solvent because we like to dissolve everything in water. And then when you mix a solute plus a solvent, you get what's called a solution, which is salt water. Salt water is a solution. If you are mixing them, why would some salt settle to the bottom and not dissolve? So let's say you have a lot of water and you put salt in there, and then not all of it dissolved. Some of it fell to the bottom. Okay? The salt, why didn't all the solute dissolve? And the key thing you need to remember from this one is because of saturation. When something is saturated, that means you cannot hold anything more in it. So if it falls to the bottom, you need to know it's because the solution is fully saturated. It cannot hold any more solute. Can't hold any more solute. Okay, Circle the substances that are not like sugar water. So sugar water is a mixture. So which one of these is not a mixture? Sand and iron fillings, that's a mixture. It's just sand and pieces of iron. Like salad, of course salad is a mixture. Salad has like tomatoes, peppers, onions, that's a mixture. Is carbon dioxide a mixture? Carbon dioxide is CO2. It's not. Carbon dioxide is a compound. Okay, it has one carbon atom and two oxygen atoms. So it is not a mixture, it is a compound. So you can circle this one. This is not like salt water. Okay, circle the one that cannot be separated into its parts by a physical or chemical change. So which one of these cannot be separated? This one has two elements, so I can separate it into Na and Cl. This one I can separate into potassium K and iodine. This one I can separate into nitrogen N and H, hydrogen, if I wanted to like add heat and break the bonds up. Hydrochloric acid I can separate into hydrogen. I can break up those bonds. Carbon, it's by itself. It's its own little element on the periodic table. Just like this one, I can't break zinc down any further because it's already the smallest it can be. So the only one that can't be separated is carbon because it's an element. It's already at its purest form, or the more basic simplified form. Okay, so this is all matter, the green lab book. Now let's start getting into the blue lab book or the purple lab book. Alright, energy. You have a skateboarder up here and he goes down. So this picture starts with what kind of energy? This is called stored energy, or energy that's not being used. The fancy word you need to know for this is stored energy is potential energy. So it starts with potential energy, and he goes down the hill, he's in motion, he's moving. Energy of motion, or when things are moving, we call that kinetic energy. So you start with potential and you transform into kinetic. Alright. Photosynthesis is how plants make food. So they take light energy from the sun and they make glucose, which is their food. Glucose has C6H12O6. So this is radiant energy or light energy, and it transforms into some type of food or some type of fuel, and we call that chemical energy. Chemical energy is the energy in bonds of atoms or food or fuel. So photosynthesis takes light or radiant energy and it transforms it into chemical energy. What type of energy does this use to do work? So the wind making it move, moving is an example of mechanical energy. Mechanical energy. Alright. And then if you forget your forms of energy, just remember Mr. Cent, mechanical, radiant, chemical, electrical, nuclear, and thermal. Okay, you should be able to tell me what each of these are and give an example of each one. Look in your interactive notebook and maybe you can make a list later on. Okay, law of conservation of energy. It's like the law of conservation of mass. When energy changes from one form to the other, like radiant energy to chemical energy, or potential energy to mechanical or kinetic energy, the total energy stays the same. Okay, stays the same That's it. So energy can't be created or destroyed. It always stays the same. It only transforms from one form to another. Okay? Alright, and then after we did MRCENT, we did a little bit about circuits. So, what kind of circuit is this? It has one pathway. So if it has one pathway, it's a circle pathway. We call these a series circuit. Okay? A parallel circuit, we can draw over here. Let's just draw a quick little parallel circuit. Parallel, I think that's how you spell it. So, let's just do a really quick one. Plus, minus. Here's the load, or the battery. Okay. And then remember, parallel circuits have multiple pathways. So we can draw a light bulb here. Actually, no, this isn't the load. This is the load. The load is the light bulb. Okay, so here's the battery. Let's call it B for battery. And remember, it has multiple pathways. Okay, so parallel, multiple pathways for the electrons to travel. Series circuit. To determine which light bulb is burned out in this type of circuit, plug in the circuit and substitute new bulbs until the bulbs turn on. Okay. This is kind of weird. Basically, you need to know if you unplug a light bulb from a series circuit, the rest will turn off because it only has one pathway. In a parallel circuit, if I unscrew or take this one out, this one over here is still shining because the electrons still have a way to travel. Okay? Alright, shifting gears a little bit. If I have a ray of light over here and angle 1, it bounces off. Number 1 shows reflection, light being reflected. Okay? If this is coming in at 45 degrees, we call this the angle of incidence. Then the angle of reflection must be the same. We talked about that. So the angle of reflection is always equal to the angle of incidence. If I'm coming in at 45, I'm bouncing out at 45. So any type of bouncing off, like boing boing, that's called reflection. When the ray of light went through this object or medium, it bent. Okay? Any type of bending, remember, that's called refraction. Refraction. Okay, remember when we stuck a pen into a glass of water, the pen looked like it bent? That's refraction. Okay? Okay. Mass is measured in grams. That is the basic unit. And we use a triple beam balance to measure mass, or some type of scale. Okay? Volume is measured in milliliters, ml, or you can do capital L for liters. Okay? And it can also be measured in meters using a formula for boxes, which I think we'll talk about later, or a graduated cylinder. So we use a graduated cylinder to measure the volume of liquids. Okay? This right here is a graduated cylinder. Okay? So just remember, mass, we use grams, volume is milliliters. Mass measures amount of matter in an object, and volume measures amount of space an object takes up. Okay? Space. Okay, so remember the two types of waves we learned about? We learned about sound waves. We call these longitudinal waves, longitudinal. And the other type of wave we learned about was light waves, which are called transverse waves. Okay? If you look over here, this right here, these are transverse waves. Okay? And the longitudinal waves, let me write over here, longitudinal. They have compressions and refractions. So remember, they look like this. Compression, rarefaction, compression, rarefaction. Okay, if you want to draw that. Okay, do sound waves need a medium? Do they have to pass through something? Yes. Okay, you cannot hear me in space because space has no medium. In order for sound to travel, it needs to bounce on something and vibrate. So why? Because sound needs particles to travel and cause vibrations. Okay? You cannot travel, sound cannot travel in space because there are no particles in space for the sound waves to bounce off of. Okay? Transverse waves, they don't need a medium. They can travel through anything. So you can say, don't need medium. Okay? So, before we answer these questions, let's just label these waves real quick. I said, remember this part was compression, when they're squeezed together, and when they're spread apart, this is called a rarefaction. And this is for longitudinal or sound waves. Okay? And then from one compression to a corresponding point on another compression, we call this over here, I'm going to write WL, wavelength. And I'll write wavelength again. So this is the electromagnetic spectrum, EMS. Okay. Remember, from one crest to one crest, we can call this wavelength. Okay. The top part of a wave is called crest of a transverse wave. These are transverse waves. The bottom part of a transverse wave is called trough, like a picture. And then how tall the waves are is called amplitude. Okay. And then how often the waves show per time period is called frequency. Okay. So I can have a high frequency wave, or I can have a low frequency wave. High frequency means the waves are frequent. Okay? Low frequency means they're not as frequent. Okay? The wavelengths are longer, and then high wavelengths means short, or high frequency means short wavelengths. Low frequency means long wavelengths. Okay? Waves transfer energy along them. They don't transfer matter. Waves transfer energy along them. Okay. Compared to radio waves, so let me focus this a little. Compared to radio waves, which I just circled, gamma rays have what kind of frequencies? So radio waves are long and slow. Okay, gamma rays are very frequent. So which one has higher frequencies? Gamma. Okay, so gamma rays have higher frequencies. Why does sound travel at different speeds through different materials? It's because of density. Okay, it travels faster through solids because solids are really dense. They're like really close together. So when the sound travels, they can go boing, 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 boing really fast. So this is solids. In liquids, they are more spaced out. They are less dense. So it takes sound slower or more time to go boing, 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 boing. Okay, and then in gases, they're less dense. The particles are very far apart. So it's going to take longer to go from this boink to this boink. Okay, so solids, you need to know, are very dense, so it's easier for the sound to go boing, 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 boing across. Okay. How tightly packed the particles are is called density. Okay? And then the density formula is m, or mass, divided by volume. So if my mass is 10 grams and my volume is 2 milliliters, my density is 10 divided by 2, mass divided by volumes, 5 grams per milliliters. That's my density. Okay, we did this. When white light hits a prism, it separates the different colors of visible light. Roy G. Biv. Remember Roy G. Biv? Okay. This is an example of wave diffraction. Diffraction. Diffraction means, you're slowing it down and it's bending. So each of the colors has a different wavelength, and that's why when you put light through a prism, you see rainbows. Okay? And it's always in this order. And remember, this section is called visible light. Visible light is all the colors you can see. So that's another thing. Going back to here, you need to know what radio waves are, microwaves, infrared waves. Visible light is the smallest portion. Okay, visible light's like literally that much. And then ultraviolet UV rays can burn you. X-rays you get at the doctor's office, and we use gamma rays to fight cancer. So make sure you know these rays, or these types of electromagnetic spectral waves. Okay. This graph shows us that as temperature increases, the amount of solute, so solute is over here on the y-axis, and temperature is over here on the x-axis. So as it gets hotter, are you dissolving more or less solute? You're dissolving more. So as the temperature increases, the amount of solute that dissolves increases as well. So you need to know that generally when things get hotter, we can dissolve more of it. Okay. What is being measured here? Well, I have a graduated cylinder, so right away I know I'm measuring volume. If I was using a triple beam balance, I would be measuring mass. Okay, let's look at this. I start with how many milliliters of water? 1, 2, 3, 4, 5. So this is 5 milliliters. I drop in this rock, and the water went up to 7 milliliters. Okay, what is the name of this method? We are trying to find the volume of just this rock. Okay, this method is called water displacement. Okay, when you sit in your bathtub and the water goes up, the water is being displaced. Okay, so if I started at 5, but I ended at 7, and I ask you what's the volume of this rock, I'm not going to say 7 milliliters. No. You have to do the final volume minus the original volume. So what's the difference? So 7 milliliters minus 5 milliliters means that this little rock has a total volume of 2 milliliters. Okay? And again, this is called water displacement method. Okay. What order are they in? Draw the arrows. So grams per milliliter, I know right away that's density. If I just had grams, that would be mass. If I had milliliters, that would be volume. If I do grams slash milliliters, look, I'm doing mass divided by volume. That's a unit of density. Sometimes you'll see density as grams per centimeters cubed. Okay, same thing. Because remember, we can use meters for volume too. Objects that sink to the bottom are more dense, and objects that float at the top are less dense. So which one of these is the one at the bottom? Which one of these numbers is the most dense? It's this one, 1.2. So this one is this level right here. Okay, I'm going to write C. Okay, which solution, which of these is floating on top of C? It's the next biggest one, which is B. So let's just write over here B. Okay, what's floating on top of B? The one that's next densest. Okay, 0.7 or 0.9, which one's bigger? 0.9. So that's going to go over here. That's D. And then the one that's floating on the top is going to be the least dense. So this is the smallest number. This one's going to be floating on the top. Okay? Boom. If the star has a density of 1.1 grams per milliliters, where will it float? So if it has 1.1, that means it's more dense than A, so it's going to go through A. Is it more dense than D? Let's see. D has 0.9. Yes, it's going to go right through this. How about B? B is 1.0. This is 1.1. This is still more dense. It's still going to sink down. And then how about C? C says 1.2. It's less dense than C, so it's not going to sink to the bottom of C because it's less dense. So the star, if you drop it in, it's going to stay right here on top of C, because C has a density of 1.2 and the star has a density of 1.1. And then remember, B has a density of 1.0, D is 0.9, and then A is the less dense, it's 0.7. Alright? Okay, so this is almost everything we did in 8th grade this year. So study through this. And if you feel like you don't know something, you need to go through your interactive notebook. You have literally everything in there to make you successful for 8th grade science review.